Hello and welcome to this session. In this session, we will discuss about solving dual problems. In our earlier sessions, we have discussed about solving maximization problems using simplex method. Now we consider the linear programming problem where we have to minimize the objective function. A standard minimization problem in n variables given by x1, x2 to xn is one in which we have to minimize an objective function of the form z is equal to c1 x1 plus c2 x2 plus so on plus cn xn subject to the constraints a11 x1 plus a12 x2 plus so on plus a1n xn is greater than or equal to b1, a21 x1 plus a22 x2 plus so on plus a2n xn is greater than or equal to b2, and am1 x1 plus am2 x2 plus so on plus amn xn is greater than or equal to bn, where bi's for I equal to 1 to m are non-negative. Also, we can see that all the constraints are greater than or equal to type and not equal to or less than or equal to. All xj's are greater than or equal to 0 for j equal to 1, 2, 3 and so on till n. Let us consider an example. Minimize z equal to 2x1 plus 3x2 plus 4x3 subject to 3x1 plus 4x2 minus x3 is greater than or equal to 5, x1 minus 2x2 plus x3 is greater than or equal to 4, x1 is greater than or equal to 0, x2 is greater than or equal to 0 and x3 is greater than or equal to 0. It is a standard minimization problem. Now let us discuss dual problem. The method of solving a standard minimization problem is called the dual method. The dual method converts a standard minimization problem into a standard maximization problem. Let us see how to form dual of a given standard minimum problem. We follow the following steps to form the dual problem of a standard minimum problem. First, write the augmented matrix A of the minimum problem. Second, write the transpose of matrix A to obtain matrix B. Third, form constraints For the dual problem, from rows of matrix B, using less than equal to symbol and the new variables. Fourth is to form the objective function from the last row of matrix B. And lastly, the objective function is to be maximized. Consider the following example. Minimize z equal to 400x1 plus 450x2 subject to 5x1 plus 10x2 is greater than equal to 45, 20x1 plus 15x2 is greater than equal to 80, x1 is greater than equal to 0 and x2 is greater than equal to 0. We have to write its dual. Let us write its augmented matrix. A is equal to the matrix 5, 10, 45 written row wise, then 20, 15, 80 again written row wise, 400, 450 and 1 again written row wise. Now see in the last column we have written the right hand side constant values of the constraints and the last entry in this column is 1, that is the coefficient of z. In the first and the second column we have written coefficients of x1 and x2 respectively. In the last row we have written coefficients of x1 and x2 in the objective function. Now we take its transpose. A prime is equal to the matrix 5, 20, 400, 10, 15, 450, 45, 80 and 1. Now rows and columns have interchanged. Let us name this matrix as B. So B is equal to the matrix 5, 20, 400, 10, 15, 450, 45, 80 and 1. Let us name the new variables as y1 and y2. Now, last column are the new constants of the constraints and we will write the constraints in less than equal to symbol. So the dual problem is maximize z equal to 45 y1 plus 80 y2 subject to 5 y1 plus 20 y2 is less than equal to 400 and 10y1 plus 15y2 is less than equal to 450. y1 is greater than equal to 0 and y2 is greater than equal to 0. This is now a standard maximization problem. Let us now discuss the method of solving standard minimization problem. First, write the dual of the standard minimization problem. Since the dual is a standard maximization problem, so it will be solved using simplex method. Solving the dual will give us the solution of the dual. That is, we will obtain the solution in new variables, but we need to find the solution in the original variables. So, to find the solution of standard minimum problem, look at the last row of the final simplex table of the dual problem. The values corresponding to the slack variables in the final table will be a solution to the minimization problem. Let us consider the example. Minimize z equal to 18x1 plus 12x2 subject to 2x1 plus x2 is greater than equal to 8, x1 plus x2 is greater than equal to 6, x1 is greater than equal to 0 and x2 is greater than equal to 0. Since it is a standard minimization problem, we first write its dual. Maximize z equal to 8y1 plus 6y2 subject to 2y1 plus y2 is less than equal to 18, y1 plus y2 is less than equal to 12, y1 is greater than equal to 0 and y2 is greater than equal to 0. Now it is a standard maximization problem. So we solve it using simplex method. We follow the same method which we have discussed in our earlier session. We get the following sequence of tables using simplex method. First we add slack variables y3 and y4 to the constraints to convert them in equal to sign, and we will have the following equations. 2y1 plus y2 plus y3 is equal to 18, y1 plus y2 plus y4 is equal to 12 and minus 8y1 minus 6y2 plus z is equal to 0. So the first iteration is, from the first table we see minus 8 is most negative. So y1 is the incoming variable or the entering variable. So y1 is the pivot column. For outgoing variable, we divide the entries of the right hand side, that is RHS column, by corresponding elements in the pivot column. That is 18 divided by 2 is equal to 9 and 12 divided by 1 is equal to 12. 9 is the minimum of the two ratios, so corresponding entry 2 is the pivot element. So Y3 is the outgoing variable. Now we have to make the pivot element 1 and other entries in the pivot column equal to 0. For this, we divide the pivot row by the pivot element 2, and on row 2 we apply the row operation R2 goes to R2 minus R1, where this R1 is row obtained after dividing pivot row by 2, which is this. Here we can see that Y1 has entered the basis and Y3 is the outgoing variable. So now row 2 will become 0, 1 by 2, minus 1 by 2, 1, 0 and 3. On row 3, we apply operation R3 goes to R3 plus 8R1. So we obtain the second iteration. See here, minus 2 is the most negative, so Y2 is the incoming variable or the entering variable. And hence the pivot column. On dividing the RHS column by the pivot column elements, we get 9 divided by 1 by 2 equal to 18 and 3 divided by 1 by 2 equal to 6. We get 6 as the minimum ratio, so 1 by 2 is the pivot element and Y4 is the outgoing variable. Again making the pivot element 1 and other entries 0 in the pivot column by using elementary row operations, we obtain the third iteration. In the third iteration, we do not have any negative value in the last row corresponding to Z. So we get the solution. Our optimal feasible solution is given by Y1 is equal to 6 and Y2 is equal to 6, and we have maximize Z equal to 8Y1 plus 6Y2, which is equal to 84. But we have to find the solution of the minimization problem. Minimize Z equal to 18x1 plus 12x2 subject to 2x1 plus x2 is greater than equal to 8, x1 plus x2 is greater than equal to 6, x1 is greater than equal to 0 and x2 is greater than equal to 0. Its solution should be given by the variables x1 and x2. For this, see the last row of the final dual simplex table. See the entries for the slack variables given by y3 and y4. We have y3 is equal to 2 and y4 is equal to 4. So, y3 and y4 are slack variables for the first and the second constraints respectively. So, x1 is equal to 2 and x2 is equal to 4. So, optimal feasible solution is given by x1 is equal to 2, x2 is equal to 4 and the minimum value of z is equal to 18x1 plus 12x2 equal to 84. Also note that when a standard minimization problem and its dual has a solution, then the maximum value of the function is same as the minimum value of the function. This is called the principle of duality. Like in the above example, the maximum value by solving the dual is 84 and the minimum value of the objective function is also 84. So in this session we have discussed about solving dual problems. This completes our session. Hope you enjoyed this session.